Start. Hello and welcome everybody, and welcome to this webinar as part of UKAN plus Physical Acoustics Special Interest Group activities. It's my pleasure and honor to introduce our speaker today, Professor Sheng, Emeritus Professor of Hong Kong University of Science and Technology and an Associate of Clare Hall, Cambridge. Professor Sheng got his BSc degree in physics from Caltech in US of A and PhD from Princeton University. After a time with the Institute of Advanced Studies in Princeton, he moved to industry, and since 1994, he's been a professor of physics at Hong Kong University of Science and Technology, and he has got numerous prizes and awards during his career, and more than nearly 480 publications, which is quite a feat itself. And today's talk is about impedance matching and designing wave absorption and design wave absorption spectrum. So without further ado, I'll hand the virtual microphone to Professor Sheng.
Okay. Yeah.
Thank you.
Thank you, Sheng, for the introduction, and also thanks to Anton for the invitation, and thanks to everybody for taking your time to join this webinar. So today, in fact, I will talk about the tunable absorption spectrum for two types of acoustic waves. One is the airborne sound, and the second is the underwater acoustics. So we'll be focusing on the absorption functionalities. So during the time limit of this talk, of course, I cannot go into all the details. And for airborne sound, the details can be found in the reference on the page here, shown here, label 1. So there are 3 publications. For underwater acoustics is in 2. So let's go into it. So the aim is to have a tunable acoustic absorption spectra from resonators. Now we all know resonance is a narrow frequency band phenomenon. However, applications require broad band. So how to resolve this dilemma represents a bottleneck for the development of acoustic metamaterials, especially for applications. And of course, as I said, we'll focus in this talk on the acoustic absorption functionalities. So one useful perspective which will be utilized in this talk is to turn the narrow frequency band phenomena on its head. That is, we view each narrow band resonator as a frequency domain Lego piece. We all know, right? Lego pieces, you know, as a child, each of us may have played with Lego pieces. We can put together Lego pieces to make anything we want. So we treat the each narrow band resonator as a frequency domain Lego piece in composing the absorption spectrum. However, any resonator integration scheme should first come to terms with the constraint imposed by causality. And so I will directly go into this issue, which is the causality constraint on sound absorption. Causality means time proceeds in only one direction, towards the future, of course. And that means there's a symmetry in the time domain. And we know from Fourier transform, time and frequency are conjugate variables. And when the time asymmetry condition is imposed on the frequency domain, profound implications can emerge. And we all know nearly 100 years ago, Hans Kramer and Rolf Kronig has discovered the Kramer's-Kronig relation for the electrodynamic dielectric function. The relation is, there are two relations between the real and the imaginary parts. And that's reasonable because the imaginary part deals with dissipation. And dissipation is an irreversible process. And so it must have to do with causality. So these are related. So let's see a less well-known constraint imposed by causality on waves. And that has to do with the thickness of the absorption. By the way, this relation applies equally well to electromagnetic absorption, electromagnetic wave absorption. So here D is the sample thickness. And B effective is the bulk modulus of the sample. And B naught is the bulk modulus of the ambient medium, the matrix medium. And here it is just for airborne sound, it's just atmospheric pressure, 1 atmosphere. And it is assumed that the absorber is placed on a rigid reflecting substrate. And here A is the absorption spectrum, lambda is the wavelength, and we take the natural logarithm, integrate, and take the absolute value. And the resulting quantity is called a minimum thickness for the absorber. And for a uniformly uniform sample with sample thickness D, it must be larger than D min. And the implication of that from this is very simple. First of all, absorption can never be 100% over a broad frequency range, because that would imply infinite thickness for the absorbers. So it has to be less than 100%. The second is that if you move the frequency band of absorption to lower frequency, it requires thicker sample thickness. Okay, that's a direct implication of this relation. And we can see this from the anechoic chamber. So this is a very good anechoic chamber, probably 10 meter by 10 meter by 10 meter. It's a very large one. And there's a woman standing there. And from the scale, you can see these pyramidal absorbers are the size of a human height. They are designed to absorb low frequency sound. So this emphasizes the importance of sample size in the absorption functionality. And is not an accident, is imposed by the causality constraint. I will not derive the causality constraint. That's probably another talk, but it's available in the literature for a long time. So what we want to do here is to turn the causality constraint into a design tool. So how to do that? So first of all, we interpret this causality constraint to mean that sample thickness can be viewed as a resource for an absorber, and that resource is to be allocated among the different frequencies of the absorption spectrum. Okay. Now, if we set the given sample thickness d to the causal minimum, namely to set d is equal to d min, we can formulate a variational problem to obtain the best absorption spectrum to absorb a given noise spectrum, S of lambda, with thickness d. So S of lambda and d, they are denoted in blue to mean they are given quantities, okay, in the following. So S of lambda does not need to be a noise spectrum to be absorbed. It can mean any target spectrum, okay? So it's you can view that as a target spectrum to be absorbed. And here is the variational functional. E of mu here is the Lagrange multiplier. And A of lambda, they are denoting, it is denoting red to mean that's the desired quantity. And the first term on the right is the absorption, okay, the total absorption. The second term is a Lagrange multiplier, and the constraint is imposed in the square bracket. Okay, so the minus sign here is just to replace the absolute value sign, okay, because 1 minus a is always less than 1. So when you take a log, it's a negative value. So this variational functional with a Lagrange multiplier is very easily solved. Okay, you take the variation of the functional with respect to a, the functional differentiation, and you immediately obtain the optimal absorber spectrum is given by this expression, okay? And there are two conditions, of course. So the mu here is the only unknown, okay? Because S of lambda is given. So in order to solve for mu, of course, is well known. We just plug this A of naught into the constraint condition. So in the equation denoted here, you have the equation in which A of naught of lambda contains the Lagrange multiplier as the unknown. So you can solve this equation for the Lagrange multiplier. And then since S of lambda is known and mu is known, then the optimal absorption spectrum may be exactly obtained. So how to realize this optimal absorption spectrum? By using resonators subject to the constraint of some given thickness. Now, I want to emphasize that thickness is a very important parameter in applications, because usually for low frequency noise, especially people in application, people usually have a space constraint. Okay, they don't have large space like that of an anechoic chamber to absorb the low frequency sound, you know, and the traditional absorbers always have a monotonically increasing absorption spectrum, namely is start from 0 at a 0 frequency, and then monotonically increase as the frequency increases, okay? And the only parameter you can adjust in a traditional absorber is its thickness, okay? But with metamaterial absorbers, we can break this limit. We can break this limit, as you will see. But how do we do that with resonators? So that requires the introduction of the concept of impedance. So since usually an absorber is placed on a reflecting background, it means that impedance matching is a crucial element for high absorption. So what's impedance? Impedance basically is a barrier felt by a wave at an air material structural interface. So suppose you have a point source. On the left, you have a usual traditional material. It is incident on this material, and a little bit will penetrate, and a large amount will be reflected, like in a Hall boundary. Now, if you have a resonance that can be induced by the source, then when the source hits the boundary, it will yield. And in that sense, the sound wave will feel that it's almost no barrier. And as a result, you can achieve impedance matching. And with impedance matching, since there is no reflection and there's no transmission because it's placed on a reflecting substrate, that means you can have very high absorption, right, from energy conservation. Because in this present case, reflection plus absorption has to be equal to 1. So if there is no reflection, then absorption becomes 1 automatically. Okay, so there is a 1-to-1 correspondence between the impedance in this case and absorption. So now let's focus on the impedance for the matching purpose. So the definition of impedance, Z, you know here, is the pressure modulation. We know sound is nothing more than tiny pressure modulations together with the displacement velocity that it generates. So we denote the displacement velocity as V. Then the impedance is just the P divided by V, okay? And the Z can be equal to 0, and that's a soft boundary. And the Z equals infinity, that's a hard boundary. Now, if for airborne sound, most of the boundaries are hard boundaries. And the reason is that it is very difficult to have a condition where the impedance is much smaller than that of air. And therefore, soft boundary is difficult to achieve for airborne sound. However, for underwater acoustics, that's easy because any acoustic wave incident at the water air interface from below, from the water side, we'll see a soft boundary, basically. So from this definition of the impedance, we can convert that to relate it to Green function. Now, Green function is defined as displacement, not displacement velocity now, is displacement. So displacement velocity is just simply the displacement times frequency, okay? So with the definition of Z and Green function, we immediately deduce that G, the Green function, is just the inverse of impedance multiplied by I divided by omega, the angular frequency. And why do we want to do that? The reason is Green function can be expanded in terms of the eigenfunctions, and that is the resonances. But the resonances are always in the form of Lorentzians, and the Lorentzians are something that we can readily write down. Okay? They are in a form, for example, for a single resonator of 1 divided by big omega squared, and a big omega here is the resonator resonance frequency minus omega, small omega squared, and the small omega is the incident wave angular frequency. And the Z is the inverse of that, and multiplied by rho naught d, the sample thickness, divided by omega, multiplied by I. Okay, that's important. Now, to the right, we plot the absolute value of Z as a function of omega at exactly the resonance frequency. Z can approach at this single frequency, soft boundary, Z equals 0. But for airborne sound, we don't want exactly 0. We want to slightly deviate from that to match with the air impedance. So in other words, the lesson from here is that by using resonators, we can tune the impedance to the impedance matching condition. And that's the main thing. So now we want to compose the different Lego pieces. So let's start with the idealized case of a continuum of resonances. So let us consider a continuously distributed resonances from an infinite collection of Fabry-Perot resonators placed in parallel. You know, the Fabry-Perot resonator is a very simple item. It's just an empty pipe with one end closed and the other end open. So we want many of these pipes placed in parallel, facing the incoming wave. So let's regard these resonance as a continuous distribution, as an approximation. You know, that's the idealized case. And here we can readily write down the Z, the total impedance of such a collection. So Z naught is the impedance of air, and Z is the effective impedance of this collection. And equals 4 omega phi. Phi here is the open end of the Fabry-Perot resonator, the ratio of these openings to the total area of the Fabry-Perot resonator placed in parallel, total area. So the fraction is a non-dimensional number. Divided by pi times the integral of big omega, d of omega, and here d omega is the important thing because that's the thing we want. We call this the mode density, is how do you distribute the modes, the resonances per unit of resonant frequency in this continuum. So this is the quantity we want to derive for a tunable target absorption frequency spectrum. Okay, so this is the most important thing. So it's denoted in red. And the denominator, of course, is the Lorentzian denominator. And the beta here is the, in frequency, is the dissipation coefficient. Okay. So if we take beta goes to 0, which is usually a good approximation, then we immediately obtain the following quantity. The first term is actually the real part of the Lorentzian, but we have an I in front, so it becomes the imaginary part of Z. Okay. So it has a big omega square minus little omega square as the denominator. So the first term, integral, has an integrand that's oscillating. Okay, it's oscillating. So you can expect the oscillating integrand usually integrate to 0 very fast. And here we will always assume there is a lower cutoff frequency, because from the causality constraint, we know that the absorption cannot go to 0 frequency. So we want to impose a lower cutoff frequency, the big omega C. Okay. And I also here want to interject the fact that for the Fabry-Perot resonator, there are usually an infinite number of resonances. The lowest resonance will have a wavelength that's namely the quarter wavelength of the lowest resonance frequency is equal to the length of the Fabry-Perot resonator. So here, in this expression, we just focus on the lowest order Fabry-Perot resonance. We can take care of the higher resonances also, but that's detailed in our publication. That can be done exactly. Okay, so don't worry. But the lowest order resonance is the most important. Okay, so let's deal with that to clarify the whole algorithm. So the second term, which is the real part of the Z, contains a delta function. And that's the result of the Lorentzian form. Okay, Lorentzian form, when the imaginary part of beta, when the beta goes to 0, yields a delta function imaginary part. And here it becomes real because the I in front. So we can temporarily ignore the first part because it is an undulating function, and we just focus on the second term in order to derive the mode density, which is what we want. And then once the mode density is determined, we can go back to the first expression, okay, which has only the lowest order Fabry-Perot resonance, and we can do the integral exactly. That integral is not difficult to do once d of omega is known. So I will show you later. So the equation for mode density, that's the simplest case. Just by integrating the delta function, which is simple, we obtain a very simple differential equation. Here, z of omega is denoted in red because it can be derived from the absorption. And the phi, as I noted, is the area fraction of the openings of the Fabry-Perot resonator divided by the total area of the absorber. Okay, so z here is adjustable. That's important. And this adjustable can be related directly to A. And A here, we can use the optimal absorption spectrum that we derived earlier from the noise spectrum or the target spectrum we want to absorb. So in other words, Z here can be directly related to the target sound spectrum we want to absorb, okay? So for a simple case, most simple case, let's say we want to have total absorption, okay, beyond the cutoff frequency. Then the equation, the red Z of omega divided by Z naught is just 1. Beyond omega, small omega greater than big omega sub C, then we just get an exponential solution. So it's very simple. And here N is essentially, we can substitute back the discreteness of N, and we can have the exponential distribution of the resonance frequencies for the resonators. And from that, we can determine the length of the resonators because from the quarter wavelength condition. But here phi is still undetermined, okay? That can be determined self-consistently, again, by the causality constraint. So we can set D bar, okay, namely the average sample thickness, because for different bipolar resonances, you can have different length, right? But we can calculate the average just from the volume conservation. So we call the volume conservation derived average sample thickness D bar. And we set D bar is equal to D min. And once we have this equation, then we have a total circle of consistency. Namely, if we have D of omega, we can derive A of omega, and from that, from D min. And on the other hand, we can have D of omega, we can have the distribution of the length of the bipolar resonators. And from that, we can obtain a D bar, and we can equate that to D min. So there's a total circle of consistency. It will come back. And that total consistency turns out to be a condition for phi. So we can just solve for phi, and the whole scheme becomes totally consistent. And also consistent with the causality constraint. So once we have that, let's say we know what the mode density is. Let's say for the case of total absorption beyond the minimum cutoff, we can substitute back into the exact expression and just integrate, okay? And we can integrate the real and imaginary part. That's not a difficult integral. So on the right-hand side, we have the top side is the real and imaginary part of Z over Z naught. And you can see the imaginary part decays pretty fast. And here, small omega divided by omega 0, which is the cutoff, essentially, it should be omega C, sorry. Beyond that, so it decays, but the real part essentially goes to asymptotically, goes to 1 very quickly. It, of course, never goes to 1, but it goes to 1 asymptotically. You can see the profile is rounded because the imaginary part plays a part in absorption in this case. So it's what you call the reactance, okay? So it's rounded. And to show you the power of the above algorithm, we show a case where the traditional absorber cannot achieve. So we want to absorb the noise generated by an electrical transformer. And then 99% of the noise energy is within the range of 110 and to 560 hertz. And so this is the target noise spectrum. So we put that into the algorithm, and we generated a optimal absorption spectrum, and that's denoted by the orange line, okay, in B, okay. And the given thickness, the constraint is 10 centimeters, okay. And you can see, of course, in the equation that we have, the z of omega is no longer so simple. You have to numerically solve that equation, okay? It's because that is no longer 1. And if you do that, and you realize this, the black line is the experimental realization measured in the impedance tube. And the green line is the acoustic form, the traditional absorber, also 10 centimeters thick. And you can see it is monotonic. And below, you can see the effectiveness. COBA means the idealized case. You can absorb 12.1 dB. And in the bottom right, you can see a photo of actually use 3D printing, fabricated absorber using 60 tubes, and they are all folded. They are of different length, of course, but they are folded into a compact rectangular solid. And the absorption is 11.5 dB. And for the acoustic form, is only 3.6 dB. So you can see a huge difference. Okay, this is something beyond the traditional absorber, because you can see in the metamaterial absorber, there is a notch in the middle that cannot be achieved with the traditional absorber. Okay, so this is something to illustrate the uniqueness of the metamaterial absorber and the success of something that we can use that as a Lego piece. And you can ask, what's the black lines beyond the idealized case? That's the due to the higher order resonances in the Fabry-Perot. So they may be unwanted, but they don't hurt. Okay, they don't hurt in the present case. So we don't have to deal with that. Now you can say, okay, how about perfect broadband absorber? So this is a case. Okay, so we have a photo and also a drawing in which we show the folding of the 5-pole resonators of different length and the experimental results. You can see there is a tail below the cutoff, which deviates from the idealized case, but that's due to the limited number of resonators. Okay. Now, this application has already been commercialized. So for some of you who are, likes to listen to music, maybe you are familiar with the KEF speakers. So 2 of my students started a startup in 2014. And so after many years of lowering the fabrication cost, they now can achieve commercial competitiveness. And for a speaker, you don't want a backward propagating wave. So usually people use absorbers in the speaker cabinet to absorb that. But the maximum they can absorb is 60%. And the KE has collaborated with the student, the startup, and they successfully absorbed 99% of the ensemble from the rear of the driver. And so now that is installed in all the KEF speakers. If you listen to one, it's surprising. It really makes a difference for the music. Okay. At first, I didn't quite believe it, but it's really true. Okay, so this you can say this is a very small scale. So here is a large scale application. These are the buildings in Hong Kong. So on the top floor, they put all the pumps, fans, chillers, everything on top, and they can generate huge amount of noise. The frequency range from 200 to 2000 hertz. So in this particular application, a total of 5,000 square meters of metal material panels were used in this project. And they can reduce the noise outside of the panels, measured at 1.5 meters away, to below 55 dB. Now, 55 dB is usually regarded as very good. So no noise can be transmitted outside of the panels. And if you use rock wool, the traditional absorber, it is 68 dB. So there's a 13 dB difference. So it is very significant. So now, in the remaining time, I will just directly go into, because I don't have too much time, with impedance matched composite for underwater acoustics. Now, sound speed in water is roughly 4 to 5 times that of in air, implying underwater acoustic absorber is generally thicker than that for airborne sound. But ideally, we want the absorb to be sub-wavelengths, high absorption, and broad frequency range in performance. So sample thickness, as we have seen, is constrained. But in this case, the ambient or the matrix bulk modulus is that of water, which is very large, at least 4 orders of magnitude larger than that of air. So the thought is, if we can have an effective bulk modulus of the absorber smaller than the water, then may be possible to have a sub-wavelength underwater acoustic absorber. And that can be realized, as we will see. So we would require impedance matching again. So the impedance definition we know is the square root of rho times B, the bulk modulus. If we can make B effective small, then in order for impedance match, we want rho effective to be large. And then the two multiple together can match that of water. In other words, we want a relation, we can define a single parameter alpha such that the effective sample modulus density is higher, the modulus is smaller by the same factor. But we have a problem here, because it's very difficult to have a bulk modulus less than 10 to the 9 Pascal, even for soft rubber. So why is the rubber so soft? And the answer is very easy, because it is a Young's modulus. Okay, it's not the bulk modulus. The rubber bulk modulus is also on the order of 10 to the 9th. Okay, because when you squeeze a piece of rubber, it bulges out on the sides. That's why. Okay, so that's an important consideration. So can one substitute Young's modulus for the B effective? And the answer is yes, but there's a condition. The sample must be in the segmented structure, and each segmented piece must be in the shape of thin rods. So that's the price you pay. And we can use materials, composite materials, that can independently tune the mass density and the moduli. So we just use tungsten particles. We can easily use copper particles. That's copper granules. very small ones, okay, microns in size, and they're coated with polymer layer. And we can do that, and we can achieve composite matching, okay, in which we can use polymer to tune the Young's modulus and the particles, heavy particles, to tune for the mass density. And the advantage of that is that not only you can shorten the absorber, because now the wavelength is much shorter, and the energy density is higher by a factor of alpha. And this also means not only it can be a good absorber, but it can also be a good sensor, underwater sensor. Why? Because you just put a thin piece of piezoelectric, okay, inside each composite. And due to the short wavelengths, it will the impedance sound will induce a very large modulation of the deformation of the piezoelectric piece, thereby generate a high voltage. So you can detect the sound, underwater sound, much easier and much more accurate. So here is just to verify that one can indeed replace the bulk modulus of the sample by the Young's modulus. I'm not going to go into details, but because I don't have time, but it's trivial. Okay, so here is the integration scale scheme, and you can see it will have different length, of course. And on the right we have a figure, and in which the dashed black line indicate the power law that we have derived before in the first section of this talk. The red line is that of exactly taking into the higher order corrections, the high order resonance for the 5 Pro. And you can see that we use 9 discrete resonators, and they have different length, and each piece are separated from the neighbor by a small gap, like 50 microns. Okay, and so the average absorber thickness at 4 kilohertz is 42 times smaller than the relevant wavelengths. So it's very much sub wavelengths. And here is a simulated result. Okay, and it's almost 99%. Very good, very broadband. And here is very instructive, because you can see, okay, so each piece can absorb the incident wave at that particular frequency, but you can ask, it only has a small cross section. The incoming wave, the wavefront is a plane wave, let's say. It has a very large front area. So how can such a small cross section absorb all the incoming wave? And the reason is that each resonator has a very high density state. So the incoming plane wave, the energy, if you plot the Poynting vector energy, it will funnel into each resonant resonator. So it is a very intriguing. If you don't believe it, you can plot it. So even a small cross section can absorb an area that's much larger than its own cross section. So the average thickness is only 8.9 millimeters. And here we just, to show you, one can tune the bulk modulus, the Young's modulus in here, and the mass density, okay, separately. And here is the sample assembly, and the whole sample is nearly 1 meter by 1 meter, 0.92 meters. And this measure in the Normandy University in a large pool. Okay, this is a photo of this experiment. And you can see the length is 5.6 meter, and the depth is 3 meters, and the width is 3.6 meters. And the experimental result is like 90%, okay? And is less than the theoretical prediction by about 7%. But given this the difficulty of the samples and the inaccuracy that may exist, we consider the agreement to be extremely good. By the way, this experiment and this whole project is a collaboration between my students, Sichao Chu, Nan Gao, who is now in Valencia, and Jean-Philippe Gorby of Le Mans, and Vicente Romero de Garcia, now at Valencia, UPV, and also with the faculties at the Normandy University. So for the time being, I wish to thank you for your attention. Okay, any questions?
Well, thank you very much, Professor, for very, very interesting talk. We have time for some questions.
Yeah, I'm sorry I have gone over the time.
That's no problem. It's a great talk. So if there is any questions, please raise your hands or put it on the chat. Okay, there is a question. Is causality optimization also useful for creating thinner phase gratings or diffusers?
Or diffusers? Okay, that's a good question. I know the people at the Le Mans, like Jean-Philippe and Vicente, who has been in Le Mans for 10 years, now at Valencia, they have done a lot of work on diffusers. And although personally I've not been involved, but I think so, because all these things have to do with impedance, okay? And for diffusers, of course, you are dealing with the angles of the scattered waves. So that's a little bit different. So a question that I did not address is how about oblique incidence? So here I can take this chance to answer that. If you have oblique incidence up to like 60 degrees, it will deteriorate only slightly. But beyond 60 degrees to 70 degrees, then it just decays, okay? Because we all know at 90 degrees, there can be no absorption, okay? Yeah. So
well, thank you very much.
Yeah.
That was a question from Ruben. Another question which is similar, I think you answered, which is from Felix. Is the causality constraint applicable to oblique incidence, diffuse incidence, other more complex sound incident field, which, as you said, probably beyond 70 degrees, it may not be applicable?
Yeah, beyond 70 degrees, because we know there is a limit of 90 degrees.
Yeah, thank you. Another question is it possible to convert this approach for a high sound transmission for applications such as ADS lensing?
Aha.
So instead of absorption, you would have high transmission.
Yeah. My intuition is saying that may not involve causality, because causality means it deals with process that's irreversible. So it deals with dissipation. Now for transmission, you want minimum dissipation. So in one case, you want to maximize, and in another case, you want to minimize. Now, I don't know. I've not thought about minimizing dissipation. Because to minimize dissipation, you want to do away with excitations in materials. Because if you have a gap in excitation, then you don't have any dissipation. That's well known.
Yeah.
So the most effective way of killing dissipation is to have a gap in the excitation spectrum.
Right. Thank you very much. Another question by Elena is a simple question. Which one of the papers, you had two papers references in the title page.
Yes.
She's asking which one did you mean? Or technical?
Well, the one they all deal with the topic I gave in the first part of my talk. But the one that gives the most detail is in the applied physics one.
Okay, thank you. The one
That's a tutorial article. Yeah.
Thank you. Right. Another question: is the mechanism by which the sound is being absorbed in these cases is a completely different mechanism than viscothermal losses? I.e., is the impedance matching itself the source of absorption, or is it helping, or it is helping the viscothermal losses to convert sound to heat?
Yeah, that's a very good question, because we first have realized that the sound absorption, the total absorption, is given by the integral of the dissipation coefficient multiplied by the energy intensity of the absorber, inside absorber. Now, the usual traditional absorber deals with maximizing the absorption coefficient effective, okay, and the interfacial conditions, interfacial areas. That's why it's most of the porous. But here, we use resonators. So we increase the energy density, okay? Not necessarily the absorption coefficient. And when you have energy density very high and absorption coefficient small, they multiply together and you integrate and they still give very good absorption. So that's the point of view that we have taken. But the yeah, so basically you can say that's a slightly different approach. That's right.
Right. Well, thank you very much. Before I forget, can I remind people that the YouTube, the video of this recording of this talk will be available in YouTube, UKAN Plus's YouTube channel in due course shortly. Thanks so much. Any other question? Oh, yes, sorry, there's another one. Can you just expand a bit on the point you made regarding the absorber's aperture being less than wavefront, being highly effective?
Oh, yeah.
Is this assuming incident wave perpendicular to the absorbers, or does this have angle dependence? Well, of course, it put them on.
No. It's when I mentioned that the energy for a plane wave normally incident, they will funnel into the resonator at that frequency of the incident wave. That is at a normal instance. But for oblique incidence, I think the similar thing is going to occur. It's just like a sink. It will just funnel the energy into that. Okay. So it's not particularly relevant to the that picture of funneling the energy into a resonator is not particularly relevant to the incident angle. So the incident angle is another consideration, of course.
Thank you very much. Right. I think we don't have any more questions. Any raised hands? No. Well, in that case, yeah, no open questions. In that case, it remains for me to thank Professor Sheng for a very interesting talk, and and again, reminder that the recording of this will be available in YouTube channel. I certainly will go back and watch it again just to remind myself what it is. And thank you for a very interesting talk, Professor.
Okay, thank you very much.
Thank you.
Thank everybody. Okay.
Thank you.
Yeah.
Bye-bye.